Deep in the cosmos lies TON 618, a black hole so enormous it defies imagination, over 60 billion times the mass of our Sun. But how can such a monster even exist, and what secrets does it hold? Today, we'll explore the largest black hole ever measured. If this fascinates you, please like, subscribe and share, and tell us in the comments, do you think even larger black holes could still be hiding out there? Thank you for watching. Now, let's begin. On the larger scales, the universe arranges itself into a connected structure known as the cosmic web, a network of filaments and voids that stretches across billions of light years and sets the lanes along which galaxies gather and grow. Within this framework, matter moves under gravity from the near emptiness of the great voids toward the denser strands, then continues along those strands into knots, where many galaxies meet and where luminous beacons switch on. These knots are not isolated objects, but the places where the flow of gas, dust and stars has been strongest for billions of years, building the conditions needed for sustained activity at galactic centers. One such beacon, TON 618, marks an extreme case in this landscape, and serves here as a reference point for the widest context. As the web developed from small irregularities in the young universe regions that were slightly denser drew in more matter, while regions that were slightly emptier gave up their contents, and the contrast slowly sharpened. Sheets of galaxies formed first, then elongated into lines, and finally collected into nodes. This sequence left behind cavities so wide that hundreds of millions of light years can pass without more than a few islands of light. The result is a vast lattice, thin in most places, thick at crossroads and always in motion. Gas streams slide along the strands like slow rivers guided by the pull of unseen mass that outweighs everything we can see, and the streams end where the web thickens. The supply lines are crucial because central engines at the hearts of bright galaxies need a steady delivery of fuel to remain visible across the observable universe. The quasar that anchors this discussion sits at such a junction where inflows can arrive from several directions, and the depth of the gravitational well is enough to gather new material even as older material is heated and expelled. At this outermost scale, the details of any single galaxy fade into the statistics of many, yet the pattern itself becomes the main fact structure funnels matter, and matter pays that guidance back by strengthening the structure. Observers on Earth cannot watch the web directly in a single image, but they can reconstruct it in ways that agree with one another. Maps of galaxy positions reveal long chains separated by bare regions, and measurements of how light from faraway sources is absorbed at different wavelengths outline the same pattern. Together, the methods agree on long chains of structure and broad empty regions, and the agreement is important because it sets a reliable frame for interpreting any single source. Spectral fingerprints from diffuse hydrogen trace cool streams, while counts of galaxies highlight where the streams end and both point to the same intersections. The picture holds not only nearby but also at great distance, showing that the web matured early and has continued to guide how matter falls, how halos assemble, and how bright centers are fed. In that scaffold, the densest neighborhoods are more likely to host the brightest engines, because supply and demand are both satisfied there. The beacon considered here fits that expectation. Every photon released by that source must pass through the web on its way to us, crossing the spaces between strands and threading sections of thin intergalactic gas, and the journey takes billions of years. The web is not a rigid skeleton, but a record of motion. Matter trickles in along many paths and on many timescales, from slow infall of diffuse gas to the delivery of entire galaxies that fall toward a common center. Collisions and mergers stir the contents of the host. Some material settles into extended halos, Some collects into disks and some sinks further toward the middle, where the central mass resides. Even when energy emitted by the central engine pushes material outward, the larger flows do not stop because the filaments reach far beyond the local environment and continue to replenish the surroundings. This balance between inflow and outflow is a key feature of the widest setting for any luminous nucleus. At large radius, the environment determines how often fresh gas is delivered, how much dust rides in with it, and how the host will respond as the center brightens or dims. When the outer reservoir is deep, the inner regions can be sustained for long periods, and when the reservoir is shallow, the inner regions fade. Thus, the very existence of an extreme object at a galactic core points back to the history of its surroundings and the strength of its connections to the larger grid. The luminous host in view does not sit in a quiet suburb of the universe, but at a crossing where more than one filament can deliver mass, and where the density of neighbours increases the chance of encounters that can channel gas inward. The large-scale setting also shapes how we interpret the light that leaves the source. Foreground gas along the route imprints signatures that must be accounted for before the properties of the source itself can be isolated, and only by placing the source within the web can those imprints be separated from local signals. The age of the universe when this light was emitted was younger than today by billions of years, which means the web then hosted more active beacons than it does now, and the rate at which gas funneled into centres was higher. Finding an unusually bright source in that era is therefore not an accident. It reflects a network that was operating at high capacity and a node that was well connected. For now, the important point at this outer edge is plain. The universe provides highways for matter. Those highways deliver fuel to nodes, and nodes nurture engines that shine strongly enough to be studied from across cosmological distances. Among those engines, the source selected here stands near the peak of observed extremes, yet its place at a node of the web follows directly from the way gravity organizes the cosmos. At the end of this wide view, the placement of TON 618 within a dense knot of the cosmic web is the essential fact because it shows that the first condition for such a powerful beacon is met before any inner detail is considered. When moving inward from the broad cosmic web, the next perspective is the position of this quasar within the observable universe. Astronomers locate it at a distance of several billion light-years from Earth, which means that the light we see today began its journey when the universe was much younger than it is now. To observe an object at such distance is to look into the past because light carries not only information, but also time itself across the expanding cosmos. The quasar appears faint in the sky through even large telescopes, yet careful measurement reveals that its brightness is extraordinary, outshining entire galaxies in visible and ultraviolet light. The fact that it can be detected at all from such an immense remove highlights how powerful its central source must be. Distances on this scale are measured through a combination of methods. The most common involves observing redshift, the stretching of light waves caused by the expansion of the universe. As light travels for billions of years, its wavelength lengthens, shifting toward the red end of the spectrum. The higher the redshift, the farther the object, and thus the earlier the time when the light was emitted. The quasar associated with the central black hole under study shows a redshift that places it billions of light-years away, giving astronomers not only a measure of distance, but also a clue to its age in cosmic history. At that epoch, quasars were more common because galaxies contained larger reservoirs of gas to feed their central engines. From Earth's viewpoint, the quasar is a point source of light. Telescopes cannot resolve its structure directly, but its spectrum reveals far more detail than an image could provide. Absorption lines appear where intervening gas has taken certain wavelengths, marking the presence of matter along the line of sight. Emission lines stand out as signatures of the fast-moving gas surrounding the central region. Together, these features allow astronomers to study not only the quasar itself, but also the matter between here and there. In this way, the quasar functions as both a target and a probe, illuminating the cosmos on its long journey. At such distance, even small uncertainties in measurement can amount to large differences in interpretation. Astronomers refine their estimates by comparing multiple methods, redshift brightness, relative to similar sources and models of cosmological expansion. The convergence of these approaches gives confidence that the quasar resides at a great but measurable remove, and that the black hole at its center reached immense mass early in the history of galaxy evolution. This is one of the striking facts about it. The central mass did not require the full age of the universe to grow, but instead must have accumulated rapidly in the first few billion years. The location within the observable universe also determines what background conditions apply. At the epoch when the light left the quasar galaxies were forming stars at a higher rate, gas clouds were more abundant and interactions between galaxies were frequent. This environment provided the fuel and the dynamical disturbances needed to drive material toward galactic centers. The quasar that harbours this largest known black hole was therefore not unusual in being active. What sets it apart is the scale of its central engine. By measuring its brightness and distance, astronomers can calculate the minimum mass required to sustain such output, and that calculation confirms that the central black hole is far larger than almost any other measured. This location is also significant in another sense. Light from the quasar has travelled across much of the observable universe, crossing cosmic time, from a period when the universe was young to the present day. Along the way, it has passed through intergalactic medium, been stretched by expansion, and preserved the conditions of the epoch when it was first emitted. Observing it is like holding a record of early cosmic history written in radiation that has not slowed or aged except by the natural expansion of space. Each photon we capture today is evidence of processes that occurred billions of years ago, fixed in the spectrum of the quasar. Understanding the position of the quasar in the observable universe is essential because it links the local extreme to the global context. The largest black hole measured so far is not only a feature of one galaxy, but also a marker of how the universe itself evolves. Its distance tells us when it shone most brightly, its redshift tells us how long the light has travelled, and its visibility tells us how powerful the central source must be. The placement of this quasar deep in cosmic time makes it a laboratory for studying both black hole growth and the conditions of the young universe. When combined, the measurements confirm that this extreme object lies billions of light years away, near the limits of what even the largest telescopes can observe in detail. Yet despite the distance, its radiation reaches Earth clearly enough to be analysed. That is the measure of its power, and also the reason it is considered a cornerstone case in understanding how black holes can reach such scale. By situating the source within the observable universe, astronomers establish not just a coordinate in space but a point in history, a record of conditions that allowed such an extraordinary central mass to form and shine. The quasar itself is a phenomenon of astonishing luminosity. A quasar is the visible manifestation of matter falling into a supermassive black hole at the centre of a galaxy, and its brightness can exceed that of entire galaxies combined. In the case under study, the quasar is so luminous that it can be detected across billions of light years, even though the light has travelled for much of the age of the universe to reach us. The radiation released is not produced by the black hole directly, since nothing can escape from within the event horizon, but by the material spiralling inward before it disappears. gas drawn toward the center heats to extraordinary temperatures, releasing energy across the electromagnetic spectrum. This outpouring of light is what defines a quasar, and what allows astronomers to identify them as beacons in distant space. The host quasar of this immense black hole radiates with an intensity that is carefully measured through surveys of the sky. Its spectrum reveals emissions in visible and ultraviolet light, as well as signatures in X-rays and infrared wavelengths. The combined output is thousands of times greater than that of ordinary galaxies, placing it among the brightest objects known. Observers note that this brightness is not steady. Quasars can vary in light over time, a result of changes in the flow of gas into the central region. These fluctuations provide valuable clues about the processes occurring near the black hole as they reflect the turbulent dynamics of matter on its inward journey. Quasars such as this are powered by the accretion of gas, which converts gravitational energy into radiation with remarkable efficiency. A small amount of mass falling into the central region can produce an enormous amount of light, far more than nuclear fusion in stars. This efficiency is why quasars can be seen across such large distances, and why they are used to probe the distant universe. The brightness of the quasar linked to this central mass is a direct indicator of the rate at which material is being consumed, though the details of the accretion flow remain a subject of careful study. The surrounding galaxy plays an essential role in sustaining such luminosity. It must deliver gas inward either through interactions with other galaxies or through internal instabilities that funnel material toward the nucleus. Observations of quasar-host galaxies often reveal disturbed structures, tidal tails, or starbursts, all signs that interactions are stirring gas and driving it toward the center. While the specific features of the host galaxy of this quasar are difficult to resolve at such distance, the intensity of its emission suggests that abundant fuel is available. This connection between galactic environment and central activity is consistent across many observations. The brightest quasars are typically associated with galaxies rich in gas and undergoing periods of dynamic evolution. The quasar also illuminates its surroundings, making otherwise invisible gas detectable. Light from the central region shines outward and ionizes material far from the black hole, producing emission lines that appear in the spectrum. These lines are key to measuring the properties of the quasar, including the speed of gas near the center and the chemical composition of its environment. In this way, the brilliance of the quasar not only announces the presence of the black hole, but also provides tools for analyzing it indirectly. Without such radiance, the black hole itself would remain invisible. Quasars occupy an important place in cosmic history. They were most common when the universe was only a few billion years old, a time when gas was plentiful and galaxy interactions frequent. The quasar associated with the largest measured black hole fits into this era, shining when conditions were optimal for rapid growth. Its continued detectability today is due to both its original power and the fact that light from that time has had billions of years to reach Earth. Thus, every observation captures a snapshot of a much earlier universe preserved in radiation that has crossed the expanding fabric of space. Astronomers classify quasars by their brightness, spectral features, and variability. This one belongs to the most luminous category, distinguished by broad emission lines that signal fast-moving gas close to the central mass. These features make it possible to estimate the mass of the black hole, since the speed of the gas depends on the gravitational pull of what lies at the center. Through such analysis, the scale of the central black hole has been established, confirming its place as the largest measured so far. The quasar's extraordinary luminosity is not simply an impressive display, but a measurable tool that allows science to probe the otherwise hidden depths of a galactic core. The light output of this quasar also influences its environment on larger scales. Radiation pressure and energetic outflows can push gas outward, slowing the rate at which new stars form in the host galaxy. This feedback process is thought to play a role in shaping the evolution of galaxies, preventing them from growing without limit and regulating the balance between black hole growth and star formation. In the case of such an extreme quasar, the influence on its surroundings would be substantial, with streams of gas heated, accelerated, and in some cases expelled from the galaxy entirely. Despite its distance, the quasar is part of a broader catalogue of sources that have been studied for decades. Each one contributes to a larger understanding of how galaxies and black holes evolve together. The quasar connected to this immense central mass stands out not only for its scale, but also for the clarity with which it demonstrates the underlying principles of quasar physics, accretion, luminosity, variability, and feedback. By placing it in context with thousands of other quasars, astronomers confirm that while it is exceptional in magnitude, it operates under the same physical processes as its less luminous peers. At this stage of description, the quasar is understood as both a lighthouse and a laboratory. It signals the presence of a central black hole that cannot be seen directly, and at the same time it provides information about that hidden object through the light it releases. TON 618 is therefore not only the largest measured black hole, but also the anchor of a quasar so bright that it bridges the gap between the unseen and the observable. The brilliance of this quasar frames the study, marking a point in the distant universe where gravitational collapse and cosmic structure combine to produce one of the most powerful sources of light known. The galaxy that hosts this quasar provides the immediate environment for the central engine. Though the glare of the quasar outshines nearly everything around it, astronomers use indirect techniques to learn about the galaxy itself and the matter clustered nearby. Host galaxies of luminous quasars are often massive, containing large stellar populations as well as abundant gas. In this case, the exact form of the host galaxy cannot be imaged in detail because of distance and brightness, yet the surrounding light and absorption features suggest a galaxy rich in matter, lying in a region where interactions with neighbours are common. The host must be substantial to sustain a central black hole of such mass, because only a galaxy of high density and deep potential can deliver enough material over billions of years. The broader galactic neighbourhood also matters. Quasars are more likely to appear in regions where galaxies are crowded because gravitational encounters can stir gas and trigger inflows toward the centres. Collisions and close passages distort stellar distributions, driving tidal forces that funnel gas inward. These processes fuel starbursts and nuclear activity alike. Evidence from other quasars at comparable distances shows that such events were frequent when the universe was young, as galaxies had not yet settled into stable structures. The host galaxy of the largest known black hole likely shared in this dynamism, with encounters supplying fresh gas to its inner regions and keeping the quasar luminous across long spans of cosmic time. Inside the galaxy, matter cycles between stars' gas clouds and the central core. Supernovae return enriched material to the interstellar medium, while cold gas collapses to form new generations of stars. At the same time, part of the gas loses angular momentum and drifts inward, adding to the supply that eventually reaches the nucleus. Observations of quasar hosts show complex mixtures of young and old stars, indicating that nuclear activity and star formation can proceed together. The extreme luminosity of the quasar in question implies that its host galaxy has managed to feed the centre, while still maintaining star-forming regions, balancing inflow against outflow in a delicate cycle. The local group of galaxies around the host is not directly visible, but clustering statistics suggest that bright quasars often lie within dense environments, similar to protoclusters. These regions are precursors of the massive clusters seen today, and they are seeded by intersections of cosmic filaments. The host galaxy of this quasar, by virtue of its location in such a knot, is expected to be accompanied by many companions. Their combined gravity shapes the motions of gas, and their interactions generate the disturbances that keep material flowing toward the center. This larger galactic context ensures that the central black hole is not starved of fuel, but continually supplied by the complex dynamics of its neighborhood. The starlight of the host galaxy, though overwhelmed by the quasar, carries important information. By decomposing the light received from the system, astronomers can separate the contribution of the quasar from that of the galaxy. This technique reveals spectral features associated with stars, giving rough estimates of stellar mass and population age. For extremely luminous quasars, the uncertainties are large, yet the presence of such features confirms that behind the bright nucleus lies a galaxy of considerable size. Without this galaxy, the quasar would lack a foundation because the black hole cannot grow in isolation. It requires a reservoir of matter sustained by the combined gravity of billions of stars. The immediate galactic surroundings also include halos of dark matter, invisible but essential. Every galaxy resides within a dark matter halo, whose mass defines the potential well that binds baryonic matter. The host of this quasar must sit in an especially massive halo one capable of gathering gas from cosmic filaments and retaining it against the pressure of radiation and outflows. Though dark matter cannot be observed directly, simulations show that halos of great mass correlate with the most luminous quasars. This link provides further context for the extreme central black hole, situating it within a system built not only of stars and gas but of invisible matter, shaping the evolution of the galaxy over billions of years. Galactic scale feedback also plays a role. Outflows powered by the quasar can extend across tens of thousands of light years, heating and dispersing interstellar gas. These winds can regulate star formation and influence the growth of the galaxy itself. The balance between feeding and feedback is complex. Inflows driven by gravitational encounters bring gas inward, while outflows driven by radiation push gas outward. The host galaxy is the arena where these processes meet, and the result determines both the future of the galaxy and the supply available to the black hole. For a quasar of such extraordinary luminosity, the struggle between inflow and feedback is intense, shaping the destiny of the entire system. The galactic neighborhood also serves as a laboratory for studying chemical enrichment. Gas observed in absorption along the line of sight carries signatures of heavy elements forged in previous generations of stars. The presence of such elements in the vicinity of the quasar demonstrates that star formation has already enriched the interstellar medium. This enrichment is important because it affects cooling rates, star formation efficiency, and the dynamics of gas inflows. The black hole at the center does not consume pristine hydrogen alone, but gas that has been cycled through stars and supernovae, linking its growth to the stellar history of the galaxy. At the boundary where the galaxy meets intergalactic space, circumgalactic material collects in vast reservoirs. These reservoirs form the transition between the galaxy and the cosmic web, acting as supply depots that can deliver fuel inward. The host of this luminous quasar almost certainly possesses such a reservoir, though it cannot be seen directly. Its existence is inferred from observations of similar systems, where streams of gas connect galaxies to their larger filaments. The connection ensures that even as the galaxy evolves, the quasar remains linked to the broader structure of the universe, drawing sustenance from scales that range from tens of light years to hundreds of millions. Thus, the host galaxy and its environment create the middle ground between the cosmic web and the innermost regions near the black hole. They provide the context in which the central mass could grow to its extraordinary size, and they anchor the luminous beacon we observe from Earth. Without this galactic setting, the quasar would not exist. The central engine is inseparable from the galaxy around it, and the galaxy is inseparable from the neighborhood that feeds it. At this scale, the quasar is not only a point of light, but also a signal of the complex structures that have nurtured it across cosmic time. TON 618 is therefore understood not as an isolated object, but as the culmination of processes that involve entire galaxies and their surroundings all converging on a single brilliant core. Beyond the visible stars of the host galaxy lies an extended region of diffuse gas known as the circumgalactic medium. This is a vast reservoir of material that encircles the galaxy, stretching far beyond its stellar disk and blending gradually into intergalactic space. It is not uniform but patchy, containing clumps of cooler gas embedded within hotter halos that extend for hundreds of thousands of light years. For a luminous quasar such as the one under study, the circumgalactic medium plays a vital role because it provides the fuel that sustains nuclear activity over billions of years. Streams of hydrogen and helium flow inward, guided by the gravitational potential of the galaxy and its dark matter halo, replenishing the supply that the central black hole requires. Without this extended halo of gas, the quasar would soon exhaust its local stores and fade. Astronomers detect the circumgalactic medium not by imaging it directly, but by analyzing how it interacts with background light. As quasar radiation passes through surrounding gas, certain wavelengths are absorbed, leaving narrow dips in the spectrum. These absorption features reveal the presence of material that would otherwise remain invisible. In many cases, the gas is enriched with elements such as carbon, oxygen, and silicon produced by earlier generations of stars. This enrichment shows that matter is not only flowing inward, but also being expelled outward by supernovae and by quasar-driven winds cycling between the galaxy and its environment. The circumgalactic medium is therefore both a source of fuel and a sink, for outflows a dynamic system that links the galaxy to the cosmic web. The balance between inflows and outflows in this region is crucial. Gas streaming inward from intergalactic filaments can deliver cold material that cools efficiently and sinks toward the galactic center. At the same time, radiation and winds from the quasar can heat surrounding gas, driving it outward and preventing further accretion. The circumgalactic medium becomes the battleground where these opposing processes meet. For a quasar of exceptional luminosity, the influence of outflows can be substantial, yet the continued brightness indicates that inflows are still dominant, bringing more material inward than is being expelled. This delicate balance sustains the activity we observe across billions of light years. The structure of the circumgalactic medium also affects how galaxies evolve. In some cases, outflows can spread enriched material far into the halo-seeding future generations of stars with heavier elements. In other cases, inflows can arrive along narrow streams feeding the central regions directly without mixing with the halo. These processes shape the growth of both galaxies and black holes. The circumgalactic medium is therefore not a passive envelope, but an active participant in cosmic evolution. The extreme black hole studied here depends on this extended environment as much as on the immediate fuel in its host galaxy. Observations of other quasars show that circumgalactic gas can extend for hundreds of thousands of light years, often glowing faintly in emission lines, such as hydrogen Lyman alpha. Although such faint halos are difficult to detect at great distance, they provide evidence that gas reservoirs are immense. The quasar connected to the largest measured black hole is likely surrounded by a halo of similar extent, though Only absorption studies can presently confirm its presence. Every feature in the spectrum becomes a probe of this invisible environment, turning the quasar's own light into a tool for mapping the gas that feeds it. The circumgalactic medium is also where galaxies connect to the cosmic web. Filaments of intergalactic gas do not stop at the edge of the galaxy, but penetrate its halo, delivering matter along preferred directions. These filaments may appear as cold streams, narrow and dense compared to the surrounding hot gas, and they provide efficient channels for fuel delivery. In simulations, such streams can reach deep into galaxies, sometimes delivering gas close to the central regions. If such processes operate here, they help explain how the central black hole could grow so massive in the available time. Continuous feeding along cosmic filaments mediated by the circumgalactic medium ensures that the nucleus never runs out of material. The feedback loop between the quasar and its halo is equally important. Radiation from the central engine can ionize circumgalactic gas, changing its temperature and pressure. Powerful winds can drive shock waves that restructure the halo, creating shells and cavities. Yet as long as the inflow continues, the system remains active. The interplay between inflow and feedback defines the long-term evolution of the quasar, determining how long it can remain visible and how massive its central black hole can become. The circumgalactic medium thus acts as both supplier and regulator, controlling the fate of the galaxy and its luminous core. At this stage, the focus remains on the outer reaches of the galaxy, rather than on the inner accretion disk. It is here in the circumgalactic medium that the largest scale exchanges of matter take place. The halo bridges the cosmic web and the galaxy, ensuring continuity of supply while also absorbing the energy of outflows. The black hole at the heart of the quasar is a beneficiary of this system growing, because the halo delivers more material than the nucleus can repel. Without this extended environment, the brilliance of the quasar would not persist, and the central mass would remain far smaller. In summary of this region, the circumgalactic medium is the unseen architecture around the visible galaxy, filled with streams, clumps, and flows of gas that interact constantly with the quasar's light and winds. It is here that the conditions are set for continued activity here, that the tug-of-war between inflow and outflow is decided, and here that the groundwork for the growth of an extreme black hole is laid. Ton 6. 1.8 stands as an extraordinary example, not only because of its central mass, but also because of the vast and dynamic halo that must surround it, binding galaxy and web together in one continuous flow of matter across cosmic time. Moving inward from the circumgalactic medium, one encounters layers of obscuring dust and molecular gas that enshroud the central region of the galaxy. These outer shells act as both veil and filter, determining how much of the quasar's light escapes, and how it appears to observers across different wavelengths. Dust absorbs and scatters visible and ultraviolet radiation, re-emitting it in the infrared, while molecular gas marks cooler regions, where heavy elements combine to form more complex compounds. These layers are common in galaxies with active nuclei, and they play a critical role in shaping the observational signatures of quasars. For an object as luminous as this one, the surrounding dust is both a consequence of intense star formation in the host galaxy, and a byproduct of feedback from the nucleus itself. The dust and gas form what is often referred to as an obscuring structure, irregular and clumpy rather than smooth. Its geometry may resemble a thickened disk or a torus depending on the angle from which it is observed. In some orientations, this structure blocks direct light from the central engine, leaving only scattered or reprocessed radiation visible. In others, the nucleus can be seen directly with only partial absorption. This orientation effect explains why quasars can appear in different forms even though the central processes are the same. for the luminous quasar connected to the largest measured black hole. The brightness is great enough to pierce through intervening material, yet the spectrum still carries signatures of dust absorption, reminding astronomers that obscuration plays a role in what is detected. Dust grains are composed of heavier elements such as carbon, silicon, and oxygen, condensed in the outflows of stars and supernovae. Over time, these grains collect in molecular clouds, where they shield gas from radiation and allow molecules to form. Carbon monoxide, for example, becomes an important tracer of cold molecular gas detectable in millimeter wavelengths. Observations of quasars at similar distances show that large reservoirs of molecular gas surround the nuclei, providing both a source of fuel for accretion and a means of obscuration. In the case of this extreme quasar, indirect evidence points to abundant molecular gas consistent with the high rate of activity implied by its luminosity. The interplay between dust and radiation is complex. Intense quasar light can destroy dust grains, sublimating them into gas, while at the same time outflows from the nucleus can spread dust outward, enriching the surrounding galaxy. This cycle means that the obscuring layers are not static but evolve as the central engine varies in power. For an extraordinarily luminous source, the destruction of dust near the center is inevitable, but farther out the grains survive, forming the reprocessing structures that dominate infrared emission. These layers ensure that even if visible light is absorbed, the energy is not lost but redistributed, making the quasar bright across the entire spectrum. The molecular gas within these shells also responds to feedback. Winds driven by radiation pressure, or jets, can compress or disperse the gas, triggering or quenching star formation. Some regions collapse under pressure to form new stars, while others are swept clear, reducing star-forming potential. This dual role of feedback highlights the connection between black hole growth and galactic evolution. The obscuring layers are therefore not mere bystanders. They are active participants in the balance of processes that shape both the host galaxy and its central black hole. Astronomers rely on these outer layers to interpret what lies deeper inside. Absorption lines imprinted by dust and molecular gas provide information about composition, density, and motion. Emission from reprocessed light reveals how energy is distributed through the system. By piecing together these signals, scientists can infer the structure and conditions near the nucleus, even though the black hole itself remains hidden. The obscuring material thus becomes a window into the unseen, its effects both concealing and revealing the processes at work. The presence of heavy elements in these layers confirms that the galaxy has undergone multiple cycles of star formation and enrichment. Such metals are created in stars and dispersed by supernovas, eventually mixing into the interstellar medium. Their abundance in the obscuring shells demonstrates that the host galaxy is mature, having produced many generations of stars before or during the era when the quasar ignited. This history ties the growth of the black hole to the broader stellar life cycle of the galaxy, embedding the nucleus within the narrative of cosmic chemical evolution. For an object as extreme as TON 618, the sheer volume of obscuring material must be enormous. The quasar's radiation is powerful enough to heat dust tens of thousands of light years from the core, yet enough survives to leave a measurable imprint. This coexistence of intense radiation and persistent dust shows how robust these structures can be sustained by the continuous replenishment of material from star-forming regions and from the inflow of gas through the galaxy. Without such replenishment, the layers would quickly be destroyed, and the quasar's appearance would change dramatically. At this stage of description, the focus remains on the outer boundary of the nucleus rather than the inner accretion disk. These dust and gas shells form the frontier between the galaxy and the quasar, shaping what astronomers can and cannot observe. They regulate the transmission of light reprocess energy into other wavelengths, and link the activity of the central black hole to the ongoing evolution of the host. Their presence explains the wide diversity of quasar appearances, while underscoring the common underlying mechanism of accretion. The obscuring layers are therefore essential to any understanding of the system. They embody the interaction between stars, gas dust, and black hole, binding together processes that span from the life cycles of individual stars to the growth of the most massive central objects. As the narrative moves inward, the importance of these layers remains clear. They are the last structures shaped primarily by galactic processes, before the environment transitions into the direct domain of the central engine itself. In the case of TON 618, the persistence of these shells, despite the quasar's power, emphasizes the scale of the galaxy's resources and the depth of its connection to the cosmic web. Deeper inside the galaxy, closer to the nucleus than the obscuring layers of dust and molecular gas, lies a region filled with fast-moving clouds of ionized material. This is known as the broad-line region, named for the wide spectral lines that appear when astronomers examine the light of the quasar. These lines are broadened because the gas is moving at immense speeds, thousands of kilometers per second, under the influence of the central black hole's gravity. Each cloud emits radiation, as it is ionized by the intense ultraviolet and X-ray light from the accretion disk, and together they produce a complex set of spectral features. For astronomers, the broad-line region is one of the most important tools for estimating the mass of the hidden black hole, because the velocities of the clouds are a direct response to the gravitational pull they feel. The broad-line region cannot be imaged directly even with the largest telescopes, but its presence is unmistakable in the spectrum. Certain emission lines, such as those from hydrogen, carbon, and magnesium, appear unusually wide, a signal that the gas is moving at very high speeds. The widths of these lines are measured carefully and combined with estimates of the distance of the clouds from the nucleus, yielding a calculation of the central mass. This method, called reverberation mapping, when variations in the light are used, has been applied to many quasars. In the case of the quasar hosting the most massive black hole measured, the broad-line features confirm that the central mass is extraordinarily large. The structure of the broad-line region is not uniform. It is composed of countless clouds, each perhaps no larger than the solar system, moving in a chaotic distribution. Some may be on nearly circular orbits, while others are plunging inward or being pushed outward by radiation pressure. The combined effect is a turbulent and dynamic zone, constantly replenished by gas from farther out, and constantly changing in response to the central radiation. The high velocities observed demonstrate the depth of the gravitational potential, well providing indirect evidence for the scale of the black hole that cannot be seen directly. The composition of the gas is also revealing. The emission lines show that the broad-line region contains not only hydrogen, but also heavier elements such as nitrogen, oxygen, and iron. These elements were forged in earlier generations of stars and carried inward through the galaxy before reaching the nucleus. Their presence indicates that the central black hole is not fed by pristine material alone, but by enriched gas that has already been through cycles of stellar evolution. This connection ties the growth of the black hole to the larger history of the galaxy, where stars form live and die, enriching the interstellar medium before their remnants drift inward. The light from the broad-line region is variable, changing in brightness as the central engine fluctuates. When the luminosity of the accretion disk increases, the gas clouds respond by glowing more brightly, and when the luminosity fades, the emission lines weaken. By measuring the delay between the central variation and the response of the clouds, astronomers can determine the distance from the black hole to the broadline region. This distance, combined with the observed velocities, allows a direct calculation of the central mass. For the quasar under study, these measurements yield a mass so large that it ranks as the greatest confirmed so far. Despite its utility, the broadline region remains mysterious in many ways. Its exact geometry is uncertain. Some models describe it as a flattened distribution resembling a thick disk, while others treat it as more spherical or clumpy. The arrangement of clouds may even change over time as inflows and outflows reshape the distribution. Radiation pressure can drive some clouds outward, while gravity pulls others inward, creating a dynamic equilibrium. This turbulence ensures that the region is never static, but always in motion, reflecting the restless processes that dominate near a luminous quasar. The role of the broadline region in the wider system is significant. It is not merely a diagnostic tool for astronomers, but also a participant in the feedback between the black hole and the galaxy. Clouds pushed outward can deliver energy and enriched material into the surrounding medium, while clouds that fall inward contribute to the accretion flow. In this way, the region serves as both a boundary and a conduit, mediating the exchange between the central engine and its galactic host. For a black hole of unprecedented size, the broadline region must be vast and energetic, its clouds racing at extreme speeds under the influence of gravity on a scale rarely encountered elsewhere in the cosmos. Studying such regions across many quasars has revealed patterns that hold universally. The widths of emission lines scale with the luminosity of the quasar, and the size of the broadline region scales with the brightness of the central source. These relationships provide astronomers with valuable tools for estimating black hole masses across the universe, even when direct reverberation mapping is not possible. The quasar connected with the largest known black hole conforms to these relationships, but lies at the extreme upper end, demonstrating the same physical rules applied on a far larger scale. The broadline region also illustrates how indirect observation can overcome the limits of distance. While the black hole itself remains forever hidden behind its event horizon, the gas clouds it influences reveal its properties with remarkable clarity. By measuring light broadened by motion, astronomers can weigh an invisible mass billions of light-years away. This method has transformed our understanding of quasars, and in the case of this exceptional object, it has confirmed the existence of a black hole of extraordinary scale. At this stage of the journey inward, the broadline region stands as the last major structure, where the influence of the galaxy overlaps with the direct domain of the black hole. It is fed by gas arriving from farther out, yet it is shaped by the intense radiation of the nucleus. Its clouds race at speeds that defy ordinary comprehension, tracing paths dictated by gravity that dwarfs anything in familiar experience. For TON 618, the broadline region is not only a glowing halo around the hidden core, but also a key to unlocking the true measure of its mass, a measure that confirms its status as the largest black hole ever recorded. Moving still further inward, the structures of dust, molecular gas, and ionized clouds give way to a disk of matter that has organized itself into a coherent form around the central mass. This is the outer accretion disk, a broad and flattened structure of gas and plasma rotating under gravity. Material from the galaxy and its surrounding environment loses angular momentum and settles into this disk, where it begins a spiraling journey toward the black hole. The process is not immediate but gradual, with matter orbiting countless times, while friction and magnetic forces cause it to drift inward. This arrangement transforms chaotic inflows from the galaxy into an organized system that can radiate immense amounts of energy. The outer accretion disk extends across a region measured in light-years, dwarfing the solar system in size. It is relatively cool compared to the inner zones, with temperatures sufficient to emit mostly optical and ultraviolet light. This emission is what makes quasars detectable across such vast distances. The luminosity observed from the quasar under study is consistent with an accretion disk of enormous scale, one capable of processing tremendous quantities of gas. Without such a disk, the central black hole could not grow to its extraordinary mass, because only through organized accretion can matter be delivered efficiently into the event horizon. Friction within the disk plays a vital role. Gas particles orbit at different speeds depending on their distance from the center, and this differential motion creates shear. Microscopic turbulence and magnetic fields convert shear into heat, causing the gas to glow. This mechanism, known as viscous dissipation, is the primary source of the disk's radiance. Even though the gas itself is transparent, the density and turbulence generate conditions where photons scatter many times before escaping, creating a luminous surface visible from great distance. The brightness of the outer accretion disk provides direct evidence that material is actively feeding the central black hole. The disk is not perfectly uniform. Instabilities arise where pressure and density fluctuate, producing waves and spiral patterns that redistribute angular momentum. In some regions, turbulence may cause gas to clump, while in others it may thin out. These instabilities regulate how quickly matter moves inward, and they may also influence the variability of the quasar's light. Long-term monitoring of quasars shows fluctuations in brightness, which can be traced back to such changes in disk structure. For the luminous host galaxy of the most massive known black hole, these fluctuations are minor compared to its average brilliance, but they still provide useful clues about the dynamics of accretion. The outer disk also interacts with its surroundings. Radiation from the disk ionizes the broadline region above it, creating the glowing emission, features already described. Winds driven off the disk carry material away, forming part of the outflows observed in quasar spectra. At the same time, gas from the galaxy rains down onto the disk, replenishing what is lost to radiation and accretion. The disk, therefore, acts as both reservoir and distributor, mediating between the galaxy outside and the event horizon inside. Its stability over long timescales ensures that the black hole continues to grow steadily. The composition of the outer accretion disk reflects the history of the galaxy. Elements heavier than helium forged in stars appear in the gas, influencing how it cools and radiates. Such enrichment affects the opacity of the disk and the spectrum of light it produces. Observations of quasars show signatures of metals in their emission, confirming that the disks are not made of pristine primordial gas, but of material cycled through multiple generations of stars. This link between stellar evolution and black hole growth illustrates how galaxies and their nuclei evolve together, each process feeding into the other. Models of accretion disks describe their vertical structure as well as their radial extent. The disk is thick enough that photons scatter repeatedly before escaping, but thin enough compared to its radius that it resembles a flat sheet. Above and below the disk regions of hotter, less dense plasma form, contributing to the high-energy emission seen in X-rays. The outer parts of the disk, however, dominate the optical and ultraviolet output. This distribution of emission across wavelengths helps astronomers confirm the presence and structure of the disk, even though it cannot be resolved directly at such great distances. The efficiency of energy release in an accretion disk is remarkable. A small fraction of the rest mass of gas is converted into radiation, making accretion far more powerful than nuclear fusion in stars. This efficiency explains why quasars outshine galaxies and why their light can travel across the observable universe. For the quasar associated with TON 618, The energy released by its disk is immense, corresponding to a rate of accretion that must have persisted for long intervals of cosmic time. Only such sustained feeding can produce the mass observed in the central black hole. The outer disk is also a record of motion. Each particle of gas carries angular momentum, and for it to move inward, that momentum must be transferred outward. This transfer is mediated by turbulence and magnetic fields, creating a cascade of motion that ensures the disk functions as a conveyor belt for matter. Without this redistribution, gas would remain in orbit indefinitely. The fact that the black hole continues to grow confirms that the disk is effective at this task, drawing material steadily inward, across scales that stretch from light years to the very edge of the event horizon. At this stage of description, the outer accretion disk emerges as the central structure through which galactic material is transformed into radiant energy. It glows with the light that makes the quasar visible across billions of light years, and it channels the inflows that allow the black hole to increase in mass. Its vast size, dynamic instabilities, and constant interplay with its environment make it a key feature of the system, bridging the scales between the galaxy and the innermost regions. For Ton 6, 1-8, the outer disk is the luminous engine room converting gravity into light and broadcasting its presence across the cosmos. Closer to the black hole than the wide cooler regions of the outer disk, the material grows denser, hotter, and more energetic. This is the inner accretion disk, the zone where matter approaches the central mass at ever greater speeds and where gravitational energy is converted most efficiently into radiation. Temperatures rise here to hundreds of thousands of degrees high enough to produce strong ultraviolet light, and in some zones even soft X-rays. The energy released from this inner portion dominates the quasar's output, and explains how the system can be seen across billions of light years. For the black hole at the core of Ton 618, the inner disk is a furnace of continuous infall channeling streams of gas into the hidden horizon. The structure of this region is shaped by the extreme gravity of the central object. Gas orbits at relativistic speeds with matter, close to the horizon, circling in only hours or days compared to years for the outer disk. The faster orbital motion increases friction between neighbouring layers of gas-generating heat that rises sharply with decreasing radius. At these scales, the disk ceases to resemble the calm outer sheets and becomes turbulent, variable, and luminous in the extreme. The radiation pressure generated here can push back against the inflow, creating a delicate balance between gravity pulling inward and radiation pressing outward. For quasars of extraordinary brightness, this balance approaches its physical limits, with the system radiating at a significant fraction of the Eddington luminosity, the point at which outward pressure matches gravitational attraction. Variability observed in quasar light curves often originates in the inner accretion disk. Small changes in accretion rate can produce noticeable differences in output because the energy released per unit of mass is greatest here. Flickers and flares recorded in quasar observations represent the dynamic processes of the inner disk, where turbulence, magnetic fields, and instabilities continually reshape the flow of gas. These fluctuations occur on timescales far shorter than the life of the quasar, yet they provide astronomers with vital clues about the processes at work. Even though the black hole itself cannot be seen, the variability of the disk betrays the restless conditions of its immediate environment. The physics of the inner disk involves more than friction and radiation. Magnetic fields thread the plasma, twisting and reconnecting as they are dragged inward. These fields can transport angular momentum outward, enabling matter to fall inward more easily. They may also channel some gas away from the disk, launching winds that rise perpendicular to the plane. This magnetohydrodynamic activity is complex, but it is central to how accretion works. Without the interplay of magnetic fields, gas would spiral inward only very slowly. With them, the process becomes efficient enough to power a quasar of immense brightness. For TON 618, such mechanisms must be operating at the highest levels, sustaining the inflow that keeps its luminosity stable over cosmic timescales. The emission from the inner disk is shaped by both temperature and gravity. Photons generated near the horizon must climb out of the deep gravitational well, losing energy along the way. This gravitational redshift alters the spectrum, shifting light toward longer wavelengths. At the same time, the rapid orbital motion of the gas produces Doppler effects, broadening and skewing emission lines. Together, these relativistic influences create the characteristic profiles seen in quasar spectra signatures that allow astronomers to infer the behavior of matter near the edge of a black hole. The quasar under study displays such features, confirming that its light comes from gas orbiting at extreme speeds in the innermost zones. The inner disk also provides the seed photons that feed the corona, the hot tenuous region that floats above the disk and emits high-energy X-rays. Soft ultraviolet light from the disk is scattered and boosted to higher energies in the corona, a process known as inverse Compton scattering. This interaction means that the inner disk not only radiates directly, but also drives additional layers of emission that extend the quasar's spectrum into higher energies. The presence of strong X-ray output in this quasar indicates that both disk and corona are active and closely linked. Matter flowing through the inner disk ultimately crosses the last stable orbit, a critical boundary defined by relativity. Inside this orbit, gas cannot remain in a circular path but plunges directly toward the horizon. Before it crosses, however, it radiates its final bursts of energy, adding to the total luminosity. The efficiency of this process is striking up to 1/10 of the rest mass of the infalling gas can be converted into radiation. This is why quasars are so brilliant and why they can dominate the light of their host galaxies. For the most massive black hole known, the energy budget is immense, reflecting not only the scale of the inflow, but the extraordinary efficiency of the conversion. The dynamics of the inner disk also influence feedback on galactic scales. Winds driven from this region can escape the galaxy, carrying mass and energy into intergalactic space. These outflows enrich the surroundings with metals and regulate the availability of gas for future star formation. In the case of such an extreme quasar, the power of these winds must be enormous, yet they have not halted the inflow entirely, as the continued brilliance of the source proves. The balance between feeding and feedback is delicate, and in this system, feeding has clearly dominated, enabling the black hole to grow beyond all others measured. Simulations of accretion disks provide visualizations of these processes, showing gas spiraling inward, magnetic fields twisting and energy radiating outward in every direction. While no telescope can resolve the disk of a quasar billions of light-years away, the agreement between models and observations supports this picture. The observed spectrum variability and emission lines all match the expectations of a hot turbulent inner disk orbiting a supermassive black hole. For TON 618, the conclusion is clear. At the heart of its luminous quasar lies a disk of matter glowing at temperatures far beyond those found in stars powered by the relentless pull of gravity. At this stage of the narrative, the inner accretion disk stands as the final gateway before matter disappears from view. It is the most luminous, turbulent, and efficient region, where infalling gas releases the last of its energy before crossing into darkness. Its radiation has travelled across the expanding universe to reach Earth, carrying with it the signatures of relativistic motion and extreme gravity. Without the inner disk, the black hole would be invisible and the quasar undetectable. With it, TON 618 becomes not only the largest known black hole, but also one of the brightest markers of cosmic history, its inner disk blazing as a beacon across time. Above and around the blazing surface of the accretion disk lies a more tenuous and hotter structure known as the corona. This region is composed of rarefied plasma energized by magnetic turbulence that rises from the disk itself. Though far less dense than the disk, the corona reaches temperatures of millions of degrees high enough to scatter photons into X-ray energies. The radiation that emerges from this layer is crucial to the overall spectrum of a quasar, because it extends the emission beyond ultraviolet light into the high energy range. For astronomers, the presence of a strong X-ray component confirms that the innermost regions are dominated not only by gravitational heating, but also by magnetic processes that accelerate particles to extreme energies. The corona is difficult to define in exact shape because it cannot be imaged directly. Theories describe it as a patchy fluctuating atmosphere above the disk where magnetic fields loop upward, reconnect and release energy. Each reconnection event heats particles which in turn collide with photons from the disk, boosting them to higher frequencies. This process of inverse Compton scattering transforms soft ultraviolet light into hard X-rays. The result is an additional layer of emission that varies with time, sometimes flickering on timescales of hours to days, reflecting the restless nature of the corona. For a quasar as luminous as the one housing the largest known black hole, the corona must be both powerful and extended, contributing significantly to the total output. The X-rays produced by the corona serve as probes of the innermost disk. When these energetic photons strike the dense material of the disk, they can be absorbed and re-emitted, creating fluorescent features in the spectrum. One of the most notable is the iron K line, a broadened and skewed signal that reveals how gravity distorts light near the black hole. These features allow astronomers to study relativistic effects at scales otherwise unreachable, providing indirect views of the geometry and behavior of the disk. In the quasar under discussion, the detection of strong high-energy emission suggests that such interactions are taking place even if the details are blurred by distance. The variability of the corona adds further insight. X-ray brightness often changes more rapidly than optical brightness, implying that the corona is compact and dynamic. Changes in magnetic field structure can alter the amount of energy released, producing bursts or dips in emission. Monitoring these changes across many quasars has shown patterns that link the behavior of the corona to the accretion rate of the disk. For the quasar linked to TON 618, such monitoring is limited by distance, yet the observed strength of its X-rays indicates that the corona is operating at the highest levels, consistent with the extraordinary mass of the central object. The role of the corona is not confined to radiation. It may also be involved in launching winds and outflows that carry matter away from the disk. As magnetic fields reconnect and release energy, they can accelerate particles to velocities sufficient to escape the gravitational pull of the black hole. These winds contribute to the larger feedback loop influencing the circumgalactic medium and regulating the supply of gas available for future accretion. The corona is therefore both a radiator and a driver of motion, shaping the environment around the black hole on multiple scales. The interaction between the disk and the corona is continuous. Soft photons from the disk enter the corona, are scattered into X-rays, and then return to strike the disk again, where they may be absorbed and re-emitted. This exchange creates a feedback loop of energy, ensuring that the two structures cannot be considered separately. Instead, they form a coupled system, with the disk providing fuel and photons, and the corona providing high-energy transformation. Together they create the full spectrum of quasar radiation, from infrared to X-rays, each part carrying information about conditions near the black hole. The physics of the corona is still not fully understood even in nearby systems. Its size, shape, and energy distribution remain topics of research. Some models suggest a compact region close to the black hole, while others describe a more extended layer above the disk. Observations of rapid variability favour a compact corona, but the strength of the X-ray output in luminous quasars suggests that it may extend farther. For the most massive black hole yet measured, the corona must be scaled up to match the enormity of the system maintaining intense emission across billions of years. The significance of the corona extends beyond the quasar itself. By producing X-rays, it provides one of the few means to probe the strong gravity regime near the horizon. High-energy photons are sensitive to relativistic effects, bending redshifting and delaying as they travel outward. Careful analysis of these features allows astronomers to test theories of gravity in conditions far more extreme than those found elsewhere. The quasar that hosts the largest black hole becomes through its corona not only a source of light, but also a natural laboratory for fundamental physics. At such distances, direct observation of fine detail is impossible, but the overall picture remains consistent across many systems. A luminous disk provides the primary light. A hot corona transforms part of that light into X-rays, and the interaction between the two creates the spectral signatures observed. For TON 618, this structure explains how the quasar shines so strongly across the spectrum from visible light to high energies. The corona's contribution is essential, adding the sharp edge of X-ray emission to the broad radiance of the disk. At this stage of the journey inward, the corona marks a transition from the structures that are mainly radiative to those that may also drive large-scale outflows. Its turbulence, magnetic fields, and high temperatures are signs of the restless conditions near the black hole, conditions that cannot be found anywhere else in the galaxy. Though invisible to the eye, the corona is revealed in the quasar's spectrum, flickering and glowing with energy carried from the depths of the accretion disk. Without it, the quasar would lack one of its defining features. With it, TON 618 shines as one of the most powerful X-ray sources in the universe, bridging the domains of radiation and matter as it channels energy from the edge of the abyss to the farthest reaches of space. In some quasars, the extreme environment near the black hole does more than radiate light. It also launches jets of matter that extend far beyond the galaxy. These jets are streams of plasma accelerated to nearly the speed of light, collimated by magnetic fields that thread the inner accretion disk and the corona. When they occur, they pierce through the interstellar medium, the circumgalactic halo, and even into intergalactic space, sometimes stretching for hundreds of thousands of light years. Not all quasars display such jets, and whether the quasar associated with TON 618 hosts them remains uncertain because of its immense distance. However, the possibility must be considered as the physics of jet formation is closely tied to the conditions around the largest black holes. Jets are believed to form when magnetic fields anchored in the rotating disk or the spinning black hole itself twist and accelerate charged particles outward. This process, known as the Blanford-Znayak mechanism in one theoretical description, allows energy to be extracted from the rotation of the black hole and converted into kinetic energy of the outflow. The result is a pair of narrow beams pointing in opposite directions, each carrying a fraction of the system's power away from the core. Observations of radio-loud quasars confirm that such jets can dominate the emission of a galaxy, producing lobes of radio light, where the streams terminate in intergalactic gas. If the quasar under study produces jets, they would be among the most powerful in the universe. The mass of its central black hole ensures an enormous reservoir of rotational energy, and the intensity of the accretion disk provides ample magnetic fields to channel it. Even if the jets are not directly observed, The presence of high-energy emission in the spectrum suggests that similar processes could be at work. Jets are not required for a quasar to shine, but when present they extend its influence far beyond the immediate environment, carrying energy and matter into the cosmic web. The effect of jets on their surroundings is profound. As they bore through the galaxy, they clear channels in the interstellar medium, heating and compressing gas along the way. At larger scales, they inflate vast radio lobes that can extend well beyond the host galaxy, marking their presence with synchrotron emission from electrons spiraling in magnetic fields. These lobes persist for millions of years long after the central activity has changed, leaving lasting imprints on intergalactic space. For the most massive black holes, such structures can be among the largest single features associated with a galaxy bridging scales, from the event horizon to hundreds of thousands of light years. Jets also influence the availability of fuel for future accretion. By heating and dispersing gas in the galaxy, they can limit the supply that reaches the nucleus, regulating the growth of the black hole. This feedback may explain why galaxies and black holes appear to evolve in tandem with their masses correlated, despite the enormous difference in scale. For the quasar that hosts TON 618 feedback of this kind, would be expected if jets exist, ensuring that the galaxy and the black hole remain in balance. Even if the galaxy continues to deliver material, inward outflows ensure that growth is not unlimited but moderated by the energy released. The detectability of jets at extreme distances is challenging. Their light is often strongest in radio wavelengths where telescopes can map extended lobes. At billions of light years, such detail is faint and the bright core of the quasar can dominate. Nevertheless, surveys of other quasars show that a fraction of them, particularly those with the most massive black holes, are radio loud, indicating strong jets. The position of TON 618 within this category remains uncertain, but the physics of jet production does not exclude it. Even without direct evidence, the possibility underscores the power of processes operating in the inner regions of the system. The formation of jets requires not only magnetic fields, but also a supply of charged particles. The accretion disk and corona provide both ionizing gas and generating fields as matter spirals inward. Once launched, the jets remain remarkably stable, maintaining collimation over immense distances. This stability is thought to arise from the alignment of magnetic fields and the continuous feeding of plasma from the disk. In simulations, jets emerge naturally when black holes spin rapidly, suggesting that spin is a key ingredient. For the largest measured black hole, if it possesses significant spin, the energy available for jet launching would be enormous. The consequences of such jets extend into the cosmic web itself. By injecting energy and metals into intergalactic space, they enrich and heat the filaments that connect galaxies. This process may influence how structures form on large scales, linking the activity of individual black holes to the evolution of the universe. Even though the central engine occupies only a fraction of a light year, its reach can extend across millions, a scale contrast that demonstrates the extraordinary power of relativistic outflows. Jets also serve as cosmic beacons, guiding astronomers to the most active and extreme systems. Their radio lobes can remain visible long after the core has faded, preserving a record of past activity. This persistence means that jets provide information not only about current conditions, but also about the history of the black hole and its galaxy. For TON 618, if jets exist, they may already have left imprints on its surroundings that would remain detectable for billions of years. These imprints would testify to the capacity of a single black hole to shape an environment on galactic and intergalactic scales. At this stage of the description, jets represent the outward reach of processes occurring near the black hole. They are not guaranteed to be present, but when they are, they extend the influence of the nucleus far beyond its immediate environment. Their existence depends on conditions of spin magnetic fields and plasma supply, all of which may be satisfied in a quasar of such extreme luminosity. Whether visible or hidden by distance jets remain an essential possibility in understanding the full scope of activity around the most massive black hole yet measured. TON 618 through its quasar may therefore not only radiate light, but also propel matter outward at near light speeds, bridging the abyss between the smallest scales of relativity and the largest structures of the cosmos. Within the region, just beyond the event horizon, lies a zone where the effects of relativity dominate. Here, the innermost stable circular orbits dictate the behavior of matter, defining the boundary at which gas can no longer maintain steady rotation and must plunge directly toward the black hole. These orbits are set by the geometry of space-time itself, curved so deeply that paths are no longer determined by Newtonian mechanics, but by Einstein's equations. For a non-spinning black hole, the innermost stable orbit lies at 3 times the radius of the event horizon, but if the black hole spins rapidly, this orbit can move closer, allowing matter to approach nearer before falling in. The location of this boundary determines the efficiency with which accretion converts mass into radiation, and it is therefore central to the luminosity of quasars. In this domain, gas particles move at significant fractions of the speed of light. The velocities are so high that time dilation becomes significant, with processes appearing slower to a distant observer than to one riding alongside the gas. The motion also produces Doppler shifts, with light from gas moving toward the observer appearing bluer, while light from gas moving away appears redder. Combined with gravitational redshift, these effects stretch and skew the emission lines in ways that can only be explained by relativistic motion near a massive object. Quasar spectra display these characteristic line profiles, confirming that matter in their inner disks is orbiting at relativistic speeds within the curved geometry of strong gravity. The innermost stable orbits are also sensitive to the spin of the black hole. A rapidly rotating black hole drags space-time around, with it a phenomenon known as frame dragging. This effect pulls the orbits of nearby matter into alignment with the black hole's spin, reducing the radius of the innermost orbit for co-rotating gas. The closer the gas can orbit, the more energy it releases before crossing the horizon. In practice, this means that the efficiency of accretion depends on spin, with rapidly rotating black holes shining more brightly for the same rate of accretion. For the most massive black hole yet measured, whether it spins rapidly or slowly remains uncertain, but its luminosity suggests that accretion is highly efficient, perhaps indicating significant spin. The physics near the innermost orbits also influences the structure of the corona and the launching of jets. Magnetic fields anchored in the disk are twisted more strongly where space-time is dragged, and this twisting can channel energy outward. Thus, the conditions in this relativistic zone determine not only the light emitted, but also the mechanical energy transported into the galaxy and beyond. Even though the region is only a few light-hours across, its effects ripple outward to scales of millions of light-years. Astronomers study the innermost stable orbits by examining X-ray spectra. Photons emitted from the inner disk are distorted by Doppler shifts and gravitational redshift, creating broad features that cannot be explained by any other mechanism. The most famous of these is the broadened iron line, which appears smeared and asymmetric. The shape of this line carries information about the radius of the innermost orbit, and therefore about the spin of the black hole. Observations of quasars at great distance are challenging, but even faint detections of such features support the picture of relativistic motion close to the horizon. For the quasar housing TON 618, The immense brightness of the source provides a rare opportunity to probe such scales even across billions of light years. The dynamics in this region are also inherently unstable. Gas orbiting just outside the innermost stable orbit can be perturbed into plunging inward, releasing bursts of radiation as it falls. Magnetic turbulence can also create variability with sudden changes in accretion rate producing flares. These events contribute to the short-term variability observed in quasars, especially in X-rays. Though distant, the quasar associated with the largest black hole shows signs of variability consistent with these processes, linking its behavior to the physics of innermost orbits. Time in this zone flows differently than in the wider universe. Clocks carried by matter orbiting close to the horizon would run slower compared to those far away, a direct consequence of gravitational time dilation. To an external observer, the final approach of gas into the black hole appears to slow and fade, never quite crossing the horizon. In reality, the gas does cross, but the distortion of time means that its fall is seen only as an asymptotic fading. This paradox of perception illustrates the strangeness of relativity near massive black holes, where intuitive notions of time and space no longer apply. The innermost orbits also serve as the last stage where radiation can be emitted before matter disappears from view. Inside this boundary, energy is no longer extracted efficiently, and the inflow becomes a plunging stream into the horizon. Thus, the innermost stable orbit represents not just a mathematical limit, but also a physical transition marking the edge of the visible universe around a black hole. It defines the inner boundary of the luminous disk, the point where light is still generated and still able to escape. The brilliance of the quasar depends critically on this radius, and therefore on the relativistic physics that sets it. For TON 618, the presence of strong emission at high energies indicates that its innermost orbits are active and luminous. Whether the black hole spins rapidly or not, the gas in these orbits radiates enormous power, contributing to the light that has travelled across billions of years to reach Earth. These inner zones are smaller than the orbit of Mercury in scale, yet they produce more energy than trillions of stars combined. The contrast between size and output underscores the extreme efficiency of accretion in the relativistic regime. At this stage of the journey inward, the innermost stable orbits represent the threshold between order and collapse. They are the last region where matter can orbit in balance before plunging irreversibly inward. Their existence confirms that gravity near a black hole cannot be described by classical mechanics alone, but requires the full framework of relativity. For the most massive black hole yet measured, these orbits are scaled up to vast dimensions, but the principles remain the same. Matter, whirls at near light speed space, and time are bent into new shapes, and the energy released lights a beacon visible across the observable universe. The immense gravitational field near the black hole does not only affect the orbits of gas, but also the paths of light itself. Photons travelling through this curved space-time are bent from straight trajectories, producing a phenomenon known as gravitational lensing. Around a massive object like the one at the centre of this quasar, light, emitted from the inner disk or from the corona, can loop, bend, and even circle before escaping. To a distant observer, this bending alters the appearance of the quasar, distorting emission lines and changing the timing of light that reaches telescopes. For black holes of extraordinary scale, lensing effects are especially strong, reshaping the radiation field in ways that reveal the hidden geometry of space-time. One of the most striking consequences of this bending is the way emission lines are broadened and skewed. Photons emitted from the side of the disk moving toward the observer are boosted in energy, while photons from the receding side are diminished. At the same time, photons climbing out of the gravitational well lose energy, producing a redshift. When combined, these effects create asymmetric line profiles that cannot be produced by ordinary processes. Observations of quasars confirm such shapes, and they match predictions from models of light moving through curved spacetime. In the quasar associated with TON 618, the intensity of light ensures that even across billions of light-years, these relativistic distortions remain visible. Gravitational lensing also affects the timing of signals. Light that travels around the black hole along different paths can arrive at slightly different times, creating echoes in the emission. These time lags are minute but detectable in nearby systems, and they allow astronomers to map the geometry of the inner disk and corona. At great distances, detecting such echoes is more challenging. Yet the principle holds photons do not all take the same route, and their arrival encodes information about the spacetime curvature near the horizon. This technique, known as X-ray reverberation mapping, is one of the few tools available for probing scales smaller than the innermost stable orbits. The bending of light can even create the possibility of multiple images. In extreme cases, photons loop around the black hole before escaping, producing rings known as Einstein rings if viewed from the right angle. While these rings are more commonly seen when a foreground galaxy lenses a background source, the principle is the same. Near a black hole, the effect is localized, creating a photon sphere where light can orbit indefinitely. Photons just outside this radius may circle once or more before departing, leading to blurred and magnified features in the observed spectrum. The presence of such effects in theoretical models helps explain the precise shapes of quasar emission lines. The gravitational lensing around a quasar also influences its brightness. Photons that would otherwise travel away are bent toward the observer, enhancing the flux seen at Earth. This focusing effect, called gravitational magnification, ensures that radiation from the innermost disk contributes strongly to the observed light. For a black hole as large as TON 618, the magnification is considerable, helping explain why its quasar is visible across such enormous distances. Without lensing, some of the light would escape in other directions. With it, more reaches our instruments, carrying the signature of relativistic gravity. Lensing is not only a local effect. On larger scales, the black hole and its host galaxy can lens background sources, bending their light in ways that add complexity to observations. In practice, however, the brilliance of the quasar itself overwhelms background objects, making such detections rare. Still, the principle remains: gravity bends all light, whether emitted from the black hole's own disk or from galaxies beyond. In every case, the bending encodes information about mass and geometry, turning light into a messenger of unseen forces. Time dilation is another crucial feature near the horizon. To a distant observer, processes close to the black hole appear slowed, stretched by the distortion of space-time. Gas spiraling inward seems to take longer and longer to complete its journey, while light flickers from the inner disk appear delayed. In reality, the processes occur at their natural pace locally, but to an external view they are drawn out. This dilation contributes to the perception of variability in quasars, with rapid changes close to the horizon smeared into slower patterns as seen from Earth. The effect illustrates how deeply time itself is altered near such extreme gravity. The interplay of gravitational lensing and time dilation creates a distinctive observational fingerprint. Light curves show delays, spectra show broadened lines, and images, if they could be resolved, would show warped structures around the black hole. Though telescopes cannot yet resolve the inner regions of distant quasars, the patterns in their spectra confirm the predictions of relativity. For the black hole at the center of TON 618, these effects must be amplified by scale, making its quasar a particularly valuable case for studying the strongest gravitational fields known. These relativistic distortions remind astronomers that the quasar is more than just a bright light source. It is also a demonstration of physics in regimes unattainable on Earth. Laboratory experiments cannot reproduce conditions where gravity bends light so strongly, or where time itself slows. Quasars provide the only natural observatories for such phenomena, and the extreme case represented by this black hole pushes the limits further than any other measured system. Observing its spectrum is therefore not only an exercise in astrophysics, but also in fundamental physics, testing the predictions of general relativity under conditions near the edge of a cosmic abyss. At this stage of the inward journey, gravitational lensing and time dilation define the experience of light leaving the inner regions. Photons carry with them not only energy, but also the imprint of warped space-time. They reveal the bending, stretching, and delay imposed by gravity that is billions of times stronger than anything encountered elsewhere. For TON 618, these effects shape every observation, ensuring that the light we capture today is not a simple record of emission, but a complex portrait of relativity in action, a portrait written in broadened lines and delayed echoes across the endless distance of the cosmos. At the very threshold of invisibility lies the event horizon, the boundary that separates the observable universe from the domain where no information can escape. The event horizon is not a physical surface, but a mathematical limit, the point at which the escape velocity equals the speed of light. Once matter or radiation crosses this limit, it cannot return regardless of how much energy it possesses. For the black hole anchoring the quasar under study, this horizon is vast, spanning a diameter measured in hundreds of billions of kilometers larger than the orbits of most planetary systems. It is the largest event horizon measured to date, a frontier where the rules of classical physics give way completely to general relativity. The size of the event horizon is directly proportional to the mass of the black hole. For TON 618, the central mass is estimated to be tens of billions of times that of the Sun, producing a Schwarzschild radius so immense that light would take days to travel across it. This means that the invisible sphere enclosing the black hole could engulf multiple solar systems with ease, yet to an observer at Earth it remains a single unresolved point, known only through its effects on surrounding matter. The event horizon itself emits no light, yet the processes just outside it are among the brightest in the cosmos. The boundary defines not only the edge of observation, but also the efficiency of accretion. Gas orbiting near the horizon reaches its highest velocities, releasing its last bursts of radiation before vanishing. The closer the innermost stable orbit is to the horizon, the more energy is extracted from matter before it disappears. Thus, the properties of the horizon combined with the spin of the black hole dictate how luminous the quasar can become. In this case, the luminosity indicates that the system is operating near the upper limits of efficiency, with the event horizon acting as the final gate through which matter passes. To a distant observer, the approach of material toward the horizon appears to slow indefinitely, never quite crossing. This is an effect of gravitational time dilation. Light emitted from matter closer and closer to the horizon is redshifted to longer wavelengths, fading into invisibility. The matter itself does cross the horizon in its own frame, but the external view is one of fading and freezing. This creates the illusion of a glowing surface at the horizon, though in reality the glow is simply the last visible light from gas before it disappears. For a quasar of such intensity, this illusion contributes to the apparent brightness, adding to the complex interplay of relativity and observation. The event horizon also defines the scale of the black hole's shadow, the dark region surrounded by the photon sphere where light is trapped in unstable orbits. If such a shadow could be imaged, it would appear as a dark disk silhouetted against the bright emission of the inner accretion disk. Observations of nearer black holes such as those imaged by the Event Horizon Telescope confirm this prediction. For a system as distant as TON 618, direct imaging is impossible with current technology, but the principles are the same. The horizon carves a boundary into space-time, invisible, yet absolute, shaping the light that escapes around it. The gravitational pull at the horizon is beyond any intuitive measure. Nothing, not even light, can overcome it once the boundary is crossed. Yet paradoxically, the region just outside the horizon is one of the most luminous in the universe. This juxtaposition darkness within brilliance just beyond defines the paradoxical nature of black holes. The brightest quasars, including the one that hosts the most massive black hole, are brilliant precisely because they sit on the edge of darkness, where gravity is strongest and radiation is most efficiently released. The horizon is both the endpoint of matter and the source of observable light. For astronomers, the event horizon is not just a theoretical construct, but a measurable scale. Its size can be calculated from the observed mass of the black hole, and its presence inferred from the behavior of surrounding gas. The existence of a horizon is also one of the strongest confirmations of general relativity, showing that massive objects collapse not into hard surfaces, but into regions defined only by geometry. Every quasar spectrum that reveals broadened lines and relativistic effects is indirect evidence that such horizons exist. In the case of the largest measured black hole, the scale of the horizon is pushed to extremes, expanding the limits of what is known to exist. The horizon also raises fundamental questions about the fate of information and the nature of physical laws. While these questions extend beyond direct observation, the event horizon of such a massive black hole provides the most dramatic stage on which they can be asked. What can be said with certainty is that the horizon is real in observational terms. It defines the edge of emission, the cutoff beyond which no photon can reach us, and the absolute sink into which all in falling matter vanishes. For TON 618, this edge is unimaginably vast, a cosmic boundary enclosing a volume of space larger than many galaxies. At this stage of the inward progression, the event horizon marks the culmination of all preceding processes. Gas drawn from the cosmic web funneled through the galaxy, filtered by dust energized in the accretion disk and heated in the corona, finally disappears through this invisible boundary. The light that allows the quasar to be seen is generated just outside, but once the horizon is crossed, the trail ends. It is the natural endpoint of matter, in the gravitational field of the largest black hole ever recorded, the defining edge, where the observable universe yields to the unobservable interior. Inside the boundary marked by the event horizon, light itself cannot escape, yet just outside it lies the photon sphere, a peculiar region where gravity bends light into closed orbits. At this radius, photons can circle the black hole multiple times before either falling inward or escaping outward. For a black hole as massive as the one at the center of this quasar, the photon sphere extends across a distance larger than the orbit of Earth around the Sun, a vast ring of potential light paths held captive by gravity. Although no telescope can directly resolve such a feature at billions of light-years, its presence is revealed in the way light from the accretion disk is distorted and magnified. The photon sphere acts as a mirror of space-time, showing the consequences of extreme curvature in a region that still communicates with the outside world. Light that grazes this region can loop around the black hole more than once, creating a series of increasingly faint echoes. Each orbit delays the photon, stretching its arrival time relative to light that travelled directly outward. This delay imprints subtle features in the observed variability of the quasar signatures that astronomers can detect in X-ray reverberation mapping. Although the signals are faint at such enormous distances, the physics ensures they exist, and their presence confirms the predictions of general relativity. For TON 618, the photon sphere represents the last frontier of visibility before complete darkness. The geometry of the photon sphere also defines the silhouette of the black hole. To an observer, the boundary between light that escapes and light that falls inward creates a shadow, a dark disk, outlined by the glow of the inner accretion disk. Nearby black holes, such as those imaged by the Event Horizon Telescope, show this shadow directly a circular shape carved into surrounding radiation. For the quasar that hosts the largest black hole known, the same principle applies on a far grander scale, though the distance makes direct imaging impossible. Still, the mathematics is exact. The photon sphere traces the visible edge, and the shadow it defines would be the largest of any black hole yet measured. The photon sphere is also a reminder that space-time near a black hole is not intuitive. Photons which normally travel in straight lines are forced into curves so extreme that they can orbit like planets. These orbits are unstable, meaning that even the smallest perturbation will send the photon inward or outward, but for an instant light itself becomes trapped in gravity's grip. This peculiar condition has no counterpart in ordinary experience and exists only in the vicinity of massive black holes. The fact that such orbits can exist at all underscores how profoundly general relativity reshapes the structure of space. As matter falls inward toward the horizon, it continues to radiate until the last moment, and this light interacts with the photon sphere. Some photons are bent into circular paths, while others are deflected outward, creating patterns of distortion in the observed spectrum. The broad wings of emission lines, the skewed profiles of iron features, and the asymmetry of variability curves are all consequences of photons navigating the curved spacetime of this region. For astronomers, these distortions are not nuisances but data offering, the only means of studying conditions near the horizon of a black hole. The limits of observation are set here. Beyond the photon sphere, no photon can provide information, because once light is trapped, it cannot escape without being redirected outward. The observable universe ends at this radius with everything inside concealed by gravity, for the quasar connected to TON 618. This means that all we know comes from regions outside the photon sphere. We can measure the inflows, the emissions, the distortions, but not the interior. What happens within remains hidden, sealed by the fundamental structure of space-time. The photon sphere is also central to future tests of physics. The shape of the shadow, it defines the timing of echoes produced by looping photons, and the precise bending of light, all depend on the validity of general relativity. If alternative theories of gravity differed from Einstein's predictions, the photon sphere would betray those differences. In this way, the quasar's light becomes not only a record of accretion, but a test of fundamental law. The larger the black hole, the clearer the test, and none is larger than the subject of this study. From Earth, astronomers capture only the integrated spectrum of the quasar, yet encoded in that light are the effects of photon orbits, gravitational delays, and relativistic shifts. By analyzing these features, they extract the maximum information possible about the innermost region. The picture that emerges is consistent across all observations, a central black hole of unprecedented mass surrounded by an accretion disk, topped by a corona possibly launching jets, and bounded by an event horizon and photon sphere that dictate the limits of observation. The quasar's brilliance is the outward manifestation of processes taking place just outside those boundaries. At this final inward step, the photon sphere marks the end of the descriptive path. Beyond it lies the horizon where no light escapes and no measurement can be made. The story of TON 618 ends here, not because the object ceases to exist, but because physics sets a natural frontier. Light cannot tell us what happens inside, and so the narrative concludes at the edge of observation. What remains is the recognition that all we know of the largest black hole ever measured comes from the photons that escape this final barrier, carrying with them the imprint of curved space-time and the power of gravity at its most extreme.